Hello everyone. This is a question on LC oscillation with more than one capacitor in this LC circuit. The question reads as two capacitors of capacitance 2C and C are connected in series with an inductor of inductance L. Initially capacitors are charged that VB minus VA is 4V0. So B is at high potential here, and VC minus VD is V0. C is at high potential here. So you can assume positive plates of two capacitors are connected here. And the questions asked is, initial current in the circuit is 0. Find what is the maximum current that will flow in the circuit, potential difference across each capacitor at that instant, equation of the current flowing towards the left in the inductor is. Right. So here I have assumed the initial state according to the given condition 4V0 and 2C. There will be a charge of C into V, which will become 8C0 here, and C capacitance V0 potential difference charge will become CV0 here. This dotted line which I have shown you here is an isolated system where the total charge on the isolated system is 9CV0, 8CV0 plus CV0. And the red color what you are seeing here is the potentials which I have assumed here. So here I assumed it is 0. Here there will be increase of 4V0, here there will be decrease of V0, and here it will become 3V0. So when we see this inductor, the current will be flowing from this high potential to low potential. That's why I have shown you I am going to assume some current flowing in this direction. So at any general time, if I consider this same circuit, the isolated system charge should remain constant. So if I assume some Q charge here it should be the remaining 9CV0 minus Q charge, and some I current I am assuming it is flowing in this direction here. Right. So we will first deal with this first two questions combinedly, A and B. Right. When the current becomes maximum, if I is maximum, then definitely dA by dt value will be equal to 0. We know that if inductance is constant, the EMF developed across the inductor will be minus L into dA by dt. So when current becomes maximum, dA by dt is 0. So EMF across that will become 0. So you can just imagine that inductor is short circuited. So here I have drawn that condition when that inductor is shorted. This is very similar to two capacitors connected to each other in your capacitors chapter, where I am just calculating this V final, which is one of the question, which is the potential difference across these two capacitors. Like plates are connected, so I can use this formula C1V1 plus C2V2 divided by C1 plus C2. Substituting all that initial conditions, you will be getting that common potential as 3V0, which is the answer for the middle question. Then we want what is that maximum current. So if the common potential difference is 3V0, this is having a capacitance of 2C. So here the charge will become 2C into 3V0. Here the capacitance is C. So here the charge will become C into 3V0. So the charges are as shown in the figure. Now as we know that there is no resistor in this diagram, only capacitors and inductors which cannot dissipate any energy, I can conserve the energy of this system at any two instants. So I have taken the initial instant when there was no current, and I am taking the instant when there is maximum current and potential difference across both the capacitors has become 3V0. So you can just see this equation. These are the initial energy stored in both the capacitors. This is the final energy stored in the capacitors, and this is the energy present in magnetic field here. This is a simple equation. You can simplify it. You will be arriving at this expression for Imax from there, which will be your first question. Right. Now we will go to the third question, where they are asking what is the equation of the current flowing to the left of the inductor. Right. So we have to get an expression for this current flowing in this inductor. I am going for a general case at any random state. Here the charge is Q, here the charge is CV0 minus Q. As I told you, it is an isolated system, and some I charge is flowing in this, I current is flowing in this one. As the current is coming out of this plate, this Q will be gradually decreasing, and I can relate these two quantities as I is equals to minus dQ by dt. Here I am writing the KVL equation. Starting from here, I am going to travel in clockwise direction. So first here there will be increase of Q upon 2C. Then you are going from positive to negative plate, so there is a decrease of CV0 minus Q upon C. And then you are going to cross the inductor. I will assume that this inductor will be opposing it with an EMF of L into dA by dt. So again you are going from positive to negative terminal, so minus L into dA by dt will be equal to 0. I have just simplified it into this part by dividing it individually and clubbing these two expressions. What I am going to do here from onwards is differentiate it again. When you differentiate it again, here this 3 by 2c is a constant. Q differentiation will be is equals to minus I from this expression. This is a constant, so it will not appear here. And this will become L into d square I by dt square. So I just take this L this side, I will be getting this expression which is very similar to your SHM, where this term will indicate omega square. So the general equation for this kind of SHM equations are I is equals to I naught sin omega t plus 5, where I naught is maximum current which you have just calculated here, and this is your omega square, so omega will be square root of that term. Now to know the phi value, I will go with the boundary conditions or initial conditions, whatever you say. At t equal to 0, we know that there is no current flowing in that circuit. It was given in the question also. Even if it is not given, that is a general assumption that at t equal to 0, there is no current. So if I substitute this into this equation, 0 is equals to I naught into sin omega into 0 plus phi, which implies sin phi will be 0 or phi will be equal to 0. So this equation will simplify into I is equals to I naught sin omega t. I have just substituted the Amax which we have calculated and omega which we have calculated, and you will finally arrive into this expression. Thank you. We will come up with another video. We will discuss an interesting question about superconductors in the next video. Thank you.